I cover a lot of physics on this channel, and sometimes I try to give some credit to the lesser-known physicists for the monumental contributions that they provided to their field. None stands out more than Giancarlo Wick. As someone who has some roots in Italy, I would be remiss not to briefly mention him. Seldomly do you ever get 4 profound ideas named after yourself because of how great you were. The Wick product, Wick ordering, Wick rotation, and the Wick theorem are fundamental concepts in the area of quantum field theory that were named after him. He was an avid outdoorsman, as I am, and in 1968 he received the Ettore Majorana Prize for his work. Anyways, let's now get to Wick rotation because I know you're eager to learn about this very fascinating concept in quantum field theory. The theme that we've been seeing in this video series on quantum field theory is throwing stuff into the complex plane. For the generating functional, we are able to see that in the context of the complex plane, its real part consisted of the sum of the trajectories that was close to 0, while the imaginary part consisted of the sum of the trajectories that was much greater than 0. This gave us a nice way to visualize how constructive and deconstructive interference worked in the complex plane and how they contribute to the overall generating functional. We then moved on to the Feynman Propagator. Here we made the change that when we allowed for the temporal frequency of a particle to get rotated into the complex plane, we were then able to get a well-behaved propagator in our action. Lastly, we found that for coherent states, by allowing the expected value of the creation operator to be the complex conjugate of that for the annihilation operator, we were able to recover the harmonic oscillator model for a system with many particles. We now turn to Wick rotation. Wick rotation is often presented as just taking time and changing it into something called complex time, and seeing what its ramifications are for our propagator. Again, this is an example of throwing something into the complex plane. What's not taught in courses and online is its deeper meaning in connection to stochastics, however. Here, we are literally going to rotate time in the complex plane and see what happens. In this very simple animation, the time that we all know and love is on the real axis. As the argument in the integrand of our action gets larger, as it gets Wick rotated, the function below begins to converge, making the integration much easier. Instead of having to integrate over all of spacetime, we have to integrate over a specified region, primarily dictated by the mass of the system that we're studying. And we'll take a look at this more in the video to come, or in this video. This tells us that Wick rotation is just a mathematical trick that makes being a physicist a lot easier. But it's more than that. What we're going to see in this video is that there's a deep connection between this rotation and something called the Wiener Increment in stochastic field theory. By the end of this video, you and I are going to invent a new type of spacetime called matter time, which will help us organize our thoughts and uncover a trade-off hidden within Wick rotation itself. So let's go ahead and get started. Alright, let's go ahead and get started with Wick rotation. So this is going to hopefully be very enlightening to many of you guys who are interested in quantum field theory, not only because this is something that is fairly common, this is something that you will see almost inevitably in your quantum field theory course, or if you take some course online or something like that, you are inevitably going to see and look at Wick rotation quite a bit, but Wick rotation is also going to shed some light on something you probably haven't studied before, which is stochastics and stochastic field theory. The question of what makes something quantum and what makes something stochastic, the intersection of those two is going to be here in this very interesting topic of Wick rotation. So let's go ahead and get started with this. So we're talking about Wick rotation. Let's do a quick review because I know it's been a while since I posted anything on quantum field theory. Mostly I've been working on the QCD playlist, but so the narrative, again, that we are dealing with is we are throwing stuff into the complex plane, right? Quantum field theory, at its core, is a mathematical field theory. And to get all of the math out of the way, we need to talk about Wick rotation, because complex numbers are inherently a mathematical construct that we use that's the square root of -1, and it's used quite frequently in quantum field theory. So we're throwing stuff into the complex plane. We've been able to see how we've been able to throw the generating functional in the context of the complex plane. And here, again, we had this idea that, or this notion that we sort of stumbled across, where the generating functional, this z of j, or the partition function, however you want to call it for right now, it's a function of the sources. The source terms are j. And we were able to do an Euler expansion, use the Euler formula, to come up with this equation to really make sense of what exactly is going on with this generating functional. We found that we had this real part. This real part had canceling contributions, where the sum of the trajectories was close to 0. And then we had this non-canceling part, the non-canceling contributions. This is that sum of the trajectories that was greater than 0. Okay, and this is the non-canceling part, was the parts where we had a lot of deconstructive interference, or a lot of constructive interference, right? So we had the constructive interference going down to 0. We had deconstructive interference expanding away from 0, and this is how we made sense of the generating functional. Okay, if again you can go brush back up on the QCD on this particular topic a few videos back, if you feel so inclined to do that, because I know I've been dropping the ball on QCD. Most of what I have been focusing on is the QCD, not QFT, but also making my website, right? So the website it's golden. It's ready to go. I'm just uploading content onto it right now, and hopefully by Christmas things will get launched. But anyways, then we took the Feynman Propagator. Again, the Feynman Propagator is this thing here that helped us make sense and understand, be able to calculate propagators, right? To have a well-behaved propagator in the context of our field theories, right? So when we had that Lagrangian, for example, we had that term where we were looking for an inverse to our propagator, right? But in order to have a well-defined inverse, we needed to define this propagator in the complex plane, and we allowed the temporal frequency to go to have this complex component to it, this little nudge in the complex plane, and by doing that we were able to get a propagator that looked like this, and then things worked out for us, right? Things, the calculations after that worked. We were able to calculate stuff after that, right? So we had our generating functional, our Feynman propagator, and our coherent states, right? So if you go back to when we talked about coherent states, we were talking about how when we defined this thing being the expectation value for our annihilation operator, and we did this, we allowed for this to happen, the complex conjugate of our expectation value being being the expectation value for our creation operator, right? And so when we did that, we were able to see in an example, again, you can go back to the video and look at this, how we were able to recover the expectation value for position and momenta in our this is our harmonic oscillator model, essentially. Okay, so there's all that. We recapped everything we talked about. Let's go ahead and dive into some Wick rotation. Now, we're going to go through this in 3 ways. The first way is going to be the way that you're typically taught Wick rotation in a quantum field theory course, right? And this is sort of the non-illuminating way. And then we're going to go into another way that's going to sort of concretify, however you want to say it, into our minds, or solidify into our minds how we might be able to understand this Wick rotation a little bit better. And then in the last section, we are going to really tie this in with stochastic field theory and geometry. So stick with me here if you want to see all the way that to the end. So We're going to continue with this narrative of taking things into the complex plane, but now we're going to start talking about Wick rotation. So Wick rotation is a mathematical tool that transforms this problematic oscillating integral into a well-behaved, exponentially dampened integral. Okay, and we'll see what I mean by this. So it does this by taking time as a complex variable and rotating it 90 degrees in the complex plane. So let's see how this works. So we're going to start off with a simple Lagrangian. Simple Lagrangian is L equals our T, which is our kinetic energy, minus our potential energy, or plus the negative, or however you want to say it. Okay. But this is our Lagrangian. It's the difference between the kinetic and the potential energy of our particle. Right, so let's suppose, just for argument's sake right now, that we have no potential. It's just a freely moving particle with nothing but kinetic energy. Highly unrealistic, but it's just a sample, just a simple example right now. And so this means our action looks like this, okay? We have 1/2 mv squared, right? We take the integral of that, and that's what our action looks like. Okay, that's all fine and good. Now let's do some Wick rotation. So Wick rotation is going to be, we take our small unit, or small interval of time, and we multiply it essentially by -I, and we call time a different variable, tau. Okay, so this is a conduit for time, but it's only a conduit for time insofar as we multiply it by our -I. Okay, this means that dx dt is dx d tau times d tau dt. Okay, and then d tau dt, well, again, this is just a constant. This is just the square root of -1. And so we're able to see that dx dt is equal to I dx d tau. Okay? Super simple so far, with nothing too crazy going on. All right, so let's plug this into our action. When we do this, we get this guy right here, right? Because this dx dt is just this guy right here, right? I'll do some drawing on the whiteboard. So dx dt is right there, and then our d tau is right here, right? So that's this guy right here. All right, so far so good. What we are going to do now is just multiply everything out, right? So we have I here, we have an I here, so we have I squared. Right, so we have I here, that stays, but the I squared, this I is squared right here, right? So we get that, and then from here to here then, I squared is -1, everything else stays the same so far, and then we get this right here, right? So this I right here is just this guy right here. Just, again, it's just a constant, we're bringing it out to the front. But now, the idea here is that, well, when we do our, when we calculate our z, right? This is e to the I s, right? So we need to over h bar, right? So this exponential is just going to be this. We're just looking at the exponential right now. All right. We're just looking at the exponential, so we multiply this. We're really just multiplying both sides by I over h, right? So, or h bar. And so when we do that, we get, here's our I over h bar, and everything else is right here. And then what we can do now is we can see that I times I, that's I squared, that goes to -1, okay? So we have this guy right here now. Okay, again, nothing crazy is going on here. This is something that you'll see quite a bit as an example in your QFT course. But now we define the Euclidean action, right? So the Euclidean action is, we're going to define to be this, right? This thing is this right here, right? Because we have h over h, so that'll just go away. So this thing, so our Euclidean action, SE, is equal to IS. We'll call that SM for Minkowski, right? Because we're looking at space-time. But to not get confused, I'll just keep it IS, which is this guy right here. Okay, so this is interesting, right? So our Euclidean action is equal to I times our Minkowski action. And so we get okay, we get this. It doesn't really seem that illuminating still, right? It's not that nothing is screaming to us like, oh, this is some deep insight or anything like that. But let's continue, and we'll get closer to some really deep insight here, specifically within stochastics. When we apply the Euler-Lagrange equations to this, we just get our equations of motion, right? Because this is our Lagrangian. Our Lagrangian is just our kinetic energy, and if there's no potential energy, we just get this. So again, nothing too crazy here. Let's go to the next level of analysis and get deeper into this, right? So, okay, the next level of analysis is going to go through Wick Rotation, but in somewhat of a simpler way, but also in a way that is, I think, more illuminating, right? So, and I'm hinging on you kind of remembering what we talked about with Gaussian integrals. So if you don't remember that, you can go back to that video, but I'm only kind of hinging on that. I'm gonna try to keep this relatively self-contained. So we have this thing right here, right? So the same action. Action is just from time 1 to time final of, again, nothing with a potential added to it. This is just kinetic energy. But this is the velocity of the particle, right? So the velocity is just the change in the position over the change in the time. Okay. And what we get when, if we were to calculate a propagator for this system, is we just get something that looks like this, okay? I'm obviously skipping a lot of steps, but all those steps you can look at when we talked about calculating this thing. This thing, again, was the path integral, right? This is the path integral, or the propagator, right? It's the propagator. It's the thing that takes our system from time 1 to time 2, 3, 4, or whatever, right? So we're going from x initial and t initial to x final and t final. So the probability of that happening, that's this function k, and it's equal to some normalization factor. We don't really care about what this normalization factor is, times this, right? Again, normalization factor, we don't really care about this that much for right now, but this thing, right, this thing, when we did this, right, when we calculated our propagator, this I showed up. This I shows up in calculating the propagators, and when we square it, we get the probability of this event happening from going from state 1 to state 2 between 2 time points. But with this I shows up, and this is an oscillatory function, right, because e to the I anything, right, so e to the I theta, well, that's an oscillatory function, right? So you can't really integrate. Oh, you can integrate, right? You can integrate between 2 time points, but there's this infinity problem. There's this infinity problem happening, right? Because there's no dampening of the function. The probability over here, right? If I were to actually draw this out. If I were to draw out, again, an oscillatory function, the probability of going from here to here, that's this value right here, whatever this value is, but the probability of going from here to here is also this value, and we could see that these values are, there's no dampening, and we would like to see dampening because that would be more reminiscent of a physical system, right? So what do? Wick rotating, okay? Wick rotating gives us this, right? Because that I and it really just goes away, right? Because when we define t to be I tau, well then I times I is just -1. This negative gets put out in here, and so this is a Gaussian function, okay? So the Wick rotated propagator, right, this thing again, or Euclidean, the probability, again, of going from space-time point, or space-time event here to a space-time event here, the probability of that happening now is now confined to a Gaussian integral, and performing this integration is actually much easier to do. Okay. In time, we're seeing that the propagator does not converge, right? Again, I have typos in here. This is to say that the probability of the particle going from one state to the next in real time can be large, even if sufficiently far away from the initial starting point. However, in imaginary time, the probability dramatically drops, right? So, and we can do that, right? So if the mass is equal to 1, I did this in Python. I did some code here in some Python, and I set the mass equal to 1 arbitrary units, because these things are going to be relative to each other. So if the mass is equal to 1, we have a function that looks like this, right? This is our propagator. This again tells us the amplitude or the probability of going between two states. And we could see that it's high here, it's low here, and then when the mass is really large, it really oscillates, right? This thing really oscillates a lot. And so integrating, we'd have to integrate over all space and time to get all these probabilities, right? And these probabilities, they just blow up to infinity. Like if we add all of these up, we just get this infinity problem. So, okay, that's the fundamental problem we're trying to see. And then when we do this Wick rotation, as we saw in the animation before I started getting to the whiteboard, we were able to take this and rotate it, sort of rotate it into this, right? But we had to rotate it in the complex plane, okay? And this is a Gaussian function, right? This is a Gaussian function, and it's, again, the mass largely determines how spread out this Gaussian function is, okay? Okay, so this is some more, again, this is our Gaussian function. So this is more, to me at least, more illuminating. But now let's go even deeper. There's 4 levels of analysis here. We're going even deeper. Let's see what this looks like from a more stochastic point of view now. The stochastic point of view is we're going to start off with looking at Schrödinger's equation, and then after that we're going to talk about the Wiener increment, or the Weiner increment, however it's pronounced, and how that is going to be related to Wick rotation as well, okay? So let's go ahead and get started on that. So we're going to take this new approach to understand this idea of Wick rotation, right? It's somewhat of a theoretical thing, but once we understand this and once we're able to grasp it, it becomes much easier to understand, I think. And so let's start with the diffusion equation, right? So the diffusion equation is sometimes called the heat equation. This heat equation, again, or this diffusion equation, sometimes you'll see it as partial P, right? This is not rho. This is going to be P because it's a probability. Partial T is equal to D partial P partial X squared, right? So this is our diffusion equation, where P is the probability of a particle to be at point X at time t, right? So at point X at time t. And so more specifically, our P function, our probability function, is a function of X and time, right? Which is why we're able to do these partial derivatives. Okay, so we have the diffusion equation. Now let's consider the Schrödinger equation. So the Schrödinger equation is this thing right here, right? So you might think, okay, well, why am I jumping all the way to the Schrödinger equation now? Well, there's a deep connection here, and let's see what this is, and it's going to be through Wick rotation, right? So our Schrödinger equation, let's do a Wick rotation. Let's Wick rotate the Schrödinger equation, right? So when we Wick rotate the Schrödinger equation, we're replacing tau, or t, with I tau, right? And when we do that, these i's are essentially going to go away. We get this -1 right here because we have this in the denominator and up here in the numerator, and so we get this, and then we get this guy right here. Okay. Okay, this doesn't look like we get this ultimately, right? Because d phi d tau, and then we have our spatial derivative here in 3 dimensions. Okay, we have this thing up here. This isn't d, right? This is not. This doesn't look like a d, right? It's this. It's the Planck's constant times 2m, or divided by 2m. The diffusion, but if we say that this is the diffusion, d equals h bar over 2m, the diffusion constant is a measure of probability of the particle going from one position to the next, where a is going to be the distance between 2 positions. Now, I have a series of videos coming out for my website on stochastics and stochastic field theory, but with just taking this sort of as sort of ground truth for right now, this here is what d looks like in stochastics, right? So where w is the probability of a particle traveling to state xi plus 1, right? Well, the way we can think about this is if we have, here's our space, we divide space into increments and say our particle is right here at xi, okay, and then so here's xi plus 1. So the probability of the particle to go from here to here is going to be, we call this omega, okay, or w. And that's this w right here. And then a is just going to be the distance, right, the distance between these 2 position states. So, okay, if we set these 2 things equal, right, so omega a squared is equal to 2 over, or h bar over 2m, we get this, okay, and then we solve for a, and a is this. Okay, this is interesting, right, because this is to say that Wick rotated Schrodinger equation is the diffusion equation, where the distance between 2 points is just a really, really, really small number, right, because h bar, that's really small, then we're dividing it by something else. That's something quite large comparatively, which is the mass. But then we're also taking the square root of it. So this thing is really fucking small, right? This is really, this is that the point here is that this a, the distance here is really, 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 really small. Okay, but it's the diffusion equation nonetheless. So what does this tell us? This tells us, Wick rotating tells us that the Schrodinger equation is a diffusion equation if we Wick rotate it, okay? So Wick rotating quantum mechanics, right, that's the area of the world of the Schrodinger equation, Dirac equation, again, Dirac equation applied to its adjoint that gives us the Klein-Gordon equation. So that's all quantum, right? That's all quantum. And then we have stochastics and diffusion starting to come into the lexicon here when we do this Wick rotation. So Wick rotation is really, it's when we Wick rotate quantum mechanics, we get stochastics, right? That's one way of thinking about this. It's really, really strange, really weird, but that's what we get when we do this sort of analysis, okay? So the next thing we're going to do, the last and final thing that we're going to do here, is take a look at Wick rotation, but in a way that is geometric and really, really hammers in stochastics, okay? So let's do this last and final bit of analysis here. So the Wick rotated function is much easier to integrate because it's just a Gaussian. We've seen that already. This is why Wick rotation is so powerful. keep in mind that integrating this function does not mean that we're integrating over time. Rather, we're integrating over states, okay? With this in mind, we can see that we're going from a quantum field theory framework to a statistical field theory framework. Let's see how this works geometrically. We're going to define something called the Wiener increment. So let's talk about this. Suppose we have a particle. Okay, here's our particle. And this was like, when I took a course on stochastics and its application to biology. And this was a really good picture. I really like this picture. And this picture is, okay, this is our space with some slice in time, okay? Here's our particle. Now our particle's free to go over here, for example, okay? This isn't exactly xi, right? So this is position xi. This here would be xi plus 1, and then this over here would be xi plus 2, right? But here's the thing. So when we're talking stochastics, the language that we want to start applying here is when we allow this particle to freely bounce from here to here, we need to sort of think of dx now as not an independent variable, okay? So it's dependent on something else, okay? So the spatial component is not independent, rather how far our particle moves is a unit distance is going to be defined by dt, and something else that we're going to call the Weiner increment, okay? So this could be xi plus 1, but with a different Weiner increment defined here. So let's go into this a little bit more. ds, right? So if we just do a little bit of Pythagoras, right? So ds, so here's dx, here's dt. ds then is the length of this squared is equal to dx squared plus dt squared, right? So ds is equal to the square root of their sum, and so we can sort of rewrite things. If we rewrite this, dx is equal to dt minus ds, right? And if ds is this, well, we get this. The fact that there's a square root here is important, okay? This is just ds, right? This here is just ds. But we're going to call it dw, right? dwt. And dwt is, that's what we're going to call the Weiner increment, right? So Weiner increment. Okay, so let's continue. Another way of looking at this is to visualize this as in this way, where dx, so here's our dx, here's our unit in space, and then we have our unit in time. The square root then of d omega t, or dwt, right? Let's call that I dt, right, or d tau. And this is, if we call this I d tau, now we're starting to, this is starting to scream Wick rotation. Such that d omega t is equal to square, right, I d tau, right, so negative I d tau. The point here is that whatever we put here, whatever constant we put out here, or if we have, like, for example, if we have dt, right, so dt plus d omega t, whatever constant we put here to scale our increment, it has to go as the square root of this thing, of whatever we put out in front here, right? Because we could have some function, f of x, right? But whatever we put in front of dw, let's say b of x. Here I'll call this a of x, right? If here we have a of x, here we have b of x, d omega t. B of x has to be proportional to the square root of d tau, which is why we have that I in here. Okay, so that's exemplified to us in this square root right here, right? These things this has to have a square root if this thing doesn't have a square root. And so these two independent variables then define how far we've gone in dx. Okay, so we've effectively redefined the independent variables in the Pythagorean identity. Instead of time and space being the independent variables, time and a kick are the new independent variables, that kick being the Wiener increment. So how hard, and we can think of this function as how hard of a kick does this particle feel from the environment. Okay, and that function, that's what this function is going to tell us. This function here is going to tell us how far in time we've traveled. So those are the two independent variables. How far in time have we traveled, and how hard of a kick have we experienced? Okay, and that's going to tell us how far in space we've traveled. So think about this for a second. Space is now the dependent variable of time. Get rid of that second of time, and a kick that a particle feels. So instead of time and space being fundamental, time and matter is fundamental, right? Because we have time and space, but when we Wick rotate now, we have time and not space, right? Because space is not a fundamental thing anymore. It's the dependent variable. It's time and some kick that the matter feels, right? The electron, whatever it is, the kick that it feels. Right, so this is just a way of sort of stepping bird's eye view. And when I say matter, I don't mean this in any sort of formal sense. I mean that what's really fundamental here is random jittery motion. Those are all these particles feeling like kicks, feeling like they're getting kicked around, and then time progresses. And so for perspective one, we have time and space. That's space-time. Our second perspective now, when we do this Wick rotation, when we Wick rotate, we have matter and time. Matter feeling this random kick. So we go from the world of determinism, right? We go from this world of determinism to a world of stochastics. I think it's CH. Yeah. The world of stochastics. And this is, if we're going to get to the philosophy behind all of this, that's really what this comes down to, right? Because space and time, if we can get an equation if we get a series of differential equations for space and time, we can predict with accuracy what it's going to do in the future. Okay, that's determinism. But now we've introduced this thing that experiences random kicks that scale by the square root of d tau or dt, and these things are fundamentally random, right? They're fundamentally stochastic in nature. This internal kick that the particle feels is at the basis of Wick rotation in QFT. Another way of saying all of this is that in space-time, fluctuations spread across all of space, and they're just weighted by probabilities, right? The probabilities again being that k, right? So k of some final time and some final spatial point, right? If I'm just going to write this all out, right? These are the weights on those probabilities. Whereas when we're looking at, so with weights on the probabilities, whereas in matter time, right, I'm calling this matter time. This is not a formal thing. I'm just something that came to my mind when I was making this, but matter time fluctuations are confined to a Gaussian, which is what we've talked about now. They're confined to a Gaussian, and the rest are just hidden in the complex plane. All right, so again, as we rotate in the complex plane, we're essentially hiding more and more of this random motion to be confined, and the rest is confined in a Gaussian, okay? So this is Wick rotation, right? Wick rotation at its core is not just rotating time into the complex plane, and that's that. It's when you rotate time into the complex plane, we move from the area of quantum field theory. What's quantum? Quantum is essentially a probabilistic mechanics to a stochastic mechanics, right? Random motion. So we have quantum, stochastics, probability, random motion, determinism, random, right? This is, while these two things almost kind of seem the same, right? Yeah, you can imagine, just close your eyes for a second and imagine the quantum world. If you're well versed in quantum mechanics, what you could maybe imagine is a bunch of particles like moving around seemingly randomly, right? But there's a probability distribution, okay? But again, they're moving around seemingly randomly. They're feeling these kicks, so there must be some connection between quantum probability distributions and all this and stochastics. This is really gonna. I don't want to go too far astray here, but this is really gets put into the topic of the Langevin equation, or Langevin equation. Which is essentially, if you were to study stochastics, this is essentially asymmetric random motion. What I mean by that is that particles will tend towards a given direction, but they're still kind of all randomly moving around. Okay, so the asymmetric means it's not completely symmetric across all of space and time. There is a general push towards one direction, but again, they're all kind of moving around within each other. And that's, again, that comes to the difference between advection and diffusion and all that. We're not going to get too much into that, but this is Wick rotation, right? So Wick rotation is the link between quantum probability distributions and stochastics with their associated equations as well, and phase space and all that. But with that being said, there we go. This is Wick rotation. Make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.